Okay, this is part 2 of the lecture on section 3.6 from Math 311, a course in linear algebra at Western Illinois University. We are going to continue talking about linear transformations. Remember, those are just functions going from a space Rn to Rm with preserved vector addition and scalar multiplication. And we saw last time every such function like that can be represented by a matrix. Right now I want to start by looking at two types of linear transformations that have nice geometric interpretations, and that is projections and rotations. Those are things that we can kind of relate to. And we'll first look at projections, and really this is just, we're projecting, in this case we'll be working in R2 and projecting a point or projecting a vector into a line that goes through the origin. But in reality what we're doing is we're just projecting a vector onto another vector. And we know the formula for that. We've done this before, and that process, or that function of sending a vector to its projection, is in fact a linear transformation. So we're going to see how that works. So we're going to start with this example. We're asked to find the standard matrix for the projection of a point in R2 onto the line y equals 2x. So just to see what we're talking about here, here's the coordinate plane. Here's the line y equals 2x. And then we're asked to take an arbitrary point in R2 called xy, and of course that will correspond to a vector. And we're really just we want to project this vector into this line here. So basically we want to find this vector right here, okay, where this angle is 90 degrees, right? So in a way that, so if this is v, we'll call this vector pv, or p of v, and that's the projection. And the way we do this, so p is really our function here. It's going to be a function from R2 to R2, and p of v is really just going to be the projection of v onto the direction vector d. Okay, where v is just xy. We can write this as a column vector now. And d is the direction vector of this line. And remember, what's the direction vector of a line? Well, the slope is 2, so that means we go up 2 and over 1. So the d is if the change in x is 1, the change in y is 2. So the direction vector is 1, 2. Okay. All right. Well, the formula for the projection of v onto d is, we already know that. That's v dot d divided by d dot d. That number times d. Okay. Well, what will that be? That will be, okay, if we take the dot product of these two vectors, we have 1x plus 2y. So we can just write this as x plus 2y. And d dot d, the dot product of d with itself would be 1 times 1 plus 2 times 2, that's 5, right? Okay, and then d is just going still 1, 2. So this will be x plus 2y over 5, 2x plus 2y over 5. Or we can write this as 1/5 x plus 2/5 y, and 2/5 x plus 4/5 y. And in fact, we can write. I think we can see what the standard matrix will be. Just plug in 1 x equals 1, y equals 0, and you'll see, so the standard matrix is, well, if you plug in 1, 0, you get 1/5, 2/5. Plug in x equals 0, y equals 1, you get 2/5, 4/5. Okay. So that's the standard matrix. And sure enough, you can see that this is going to be 1/5, 2/5, 2/5, 4/5 times xy. Okay. So this is all equal to P of V, which is P of xy. Okay. All right, so we can see that, in fact, this is algebraically, after all this, because this can be represented as a matrix, this way, it's a linear transformation. You could also see, just going back to this formula here, that, for example, if we wanted to show this directly, P of, let's say, we have two vectors v1 and v2, P of v1 plus v2, well, what would that be? That would be v1 plus v2 dot d over d dot d times d. And we can actually just, we can just use the linearity of the dot product. This numerator right here can be written as v1 dot d plus v2 dot d. Okay. And for that reason, you can break this number up. So it'll be, so this will be v1 dot d over d dot d times d plus v2 dot d over d dot d times d. So this will be P of v1 plus P of v2. Okay, and then similarly, if you want to compute C of v1, where C is any real number, this will be C v1 dot d over d dot d. Okay. And then C is just a constant, so you can pull that out. So this will be Cp of v1. Okay, so P is a linear transformation. All right. So there were two ways to do that. Another transformation is rotations. And here we're going to be considering rotations. We're just rotating a vector or a point counterclockwise through a certain angle. Okay, so we'll denote r theta. Again, this is going to be, we're taking this to be transformation, taking vectors in R2 to vectors R2 by just rotating them around the origin by counterclockwise by theta degrees. Okay, so let's just see before we calculate the standard matrix for this, why is this linear transformation? Can we do this without bringing matrices in yet? Well, the reason for that is, remember, the first thing we want to show that it preserves scalar addition. Well, if we have a vector u and a vector v here, okay, the sum can be seen as the diagonal of the parallelogram that it goes, that it forms. The two vectors form, right? So if you rotate u and v, through theta degrees, then you're at the same time you're rotating u plus v, right? Because all of these are going to be moving at the same time, right? So so this parallel, maybe this whole parallelogram will be rotated over here, and I'm going to mess this up here, but yeah, so it'll be something like this. Okay, so here's So this would be r theta of u and r theta of v, and then this would be the r theta of u plus v. Okay, if you can read that, but basically you're rotating this whole everything here in this picture, but through the same angle. To show this preserved scalar multiplication, that's a little easier. If this is v, let's say this is CV, and you rotate it through a certain angle. Okay. Okay, then this vector, this will be r theta of v, and this vector will be r theta of CV, which you can see is c times r theta of v. Right? You're just you can take this and rotate it like this, or you can take the smaller vector, rotate it, and then multiply it by c. You get the same thing. Okay, so these are linear transformations. Well, the harder part might be, or another part would be finding the standard matrix of these rotations, and not surprisingly, this isn't going to involve trig functions, sines and cosines. We haven't really done a lot with trigonometry yet in linear algebra, but that's going to change right now. Let's just see now what would be, how do we define the standard matrix? Well, we basically want to find what is r theta of the standard basis vector. So r theta of 1, 0 and r theta of 0, 1. We'd like to know what these are. Okay, so how do we do that? Well, the first part's not too bad. It's really almost like the definition of sine and cosine. So remember how sine and cosine are defined. We have the unit circle here, and a certain angle theta is going to correspond to a point on this circle. If this angle is theta, then the x-coordinate is cosine and the y-coordinate is sine. Okay, and of course this point right here is 1, 0, and that actually corresponds. We can see that here's a vector, here's a vector, and when we rotate this, if the input vector is 1, 0, the output vector is going to be cosine sine. So we see that this is going to be cosine theta, sine theta. Okay. All right. Now to see what happens to the vector 0, 1. Let me remind you that 0, 1. That's this vector right here. Okay, and we want to rotate it through theta. So, okay. All right. Now, the trick, if you want to call it a trick, is you just have to see that we can form over here. We can complete this picture and draw a triangle here, where this vertical line connects this point here to the x-axis. We can basically take this whole triangle and we rotate it here. Now this is basically the same triangle. We've rotated it through 90 degrees basically. And what we do is that so what's the y coordinate here? Well, the x and y coordinate of this point. You can see that this distance right here is now equal to this distance. So the x-coordinate here is now the y-coordinate here. So this is actually going to be cosine theta will be the y-coordinate. And then the x-coordinate here is this distance, which, well, it's actually the opposite of whatever this distance is, because we can see that the x-coordinate has to be negative. But this distance is equal to this distance, and this distance was equal to the sine of theta. So this is minus sine theta. Okay, so the output is minus sine theta, cosine theta. Okay, and so the standard matrix is cosine theta, sine theta, minus sine theta cosine theta. All right, so this is the standard matrix. Of r theta. And so, for example, if theta is equal to 90 degrees, your cosine of, again, is cosine of 90 degrees is 0, sine is 1, so this is 0, 1, negative 1, 0, which we actually saw before. If theta is 45 degrees, both the sine and cosine are both equal to 1 over square root 2. Okay, and here it's really just knowing your trig values. Okay. Okay, so those are rotations. Now I want to. We're gonna see there's a nice little application of this. But before we do that, I do want to talk about compositions of linear transformations, because this topic basically justifies all this what the way we multiply matrices. So one of the benefits or the reasons why we define multiplication of matrices the way we do is we want it to be these standard matrices to be compatible with composition of their linear transformations. Let me recall what it means to compose something. If f and g are functions, then the composition of f and g is sometimes denoted f circle g, and f circle g of x is just f of g of x. Of course, this only makes sense if g of x is in the domain of f and x is in the domain of g. Otherwise, this wouldn't make sense, right? So, because linear transformations are functions, we can compose them in certain situations. If t and s are linear transformations, where t goes from takes vectors in Rn and sends them to Rm, and s takes vectors in Rm and sends them to vectors in Rp, then their composition f composed with t takes vectors in Rn and sends them to Rp. Okay. Obviously, this number, this number and this number have to be the same, and here for this to make sense. But this will be a linear transformation, and the standard matrix of the result st. We're going to write st instead of s circle t, but it means the same thing here. Okay. And the main result here is that the composition is a linear transformation, and its standard matrix will be the product of the standard matrices of the two other transformations. So let's just see why that works out. Just first to show that these are compositions. It's not hard at all. The st of v. Let's say of u plus v is going to be s of t of u plus v, which is, because t is a linear transformation, this is s of t of u plus t of v, and because s is a linear transformation, this is s of t of v, or I'm sorry, of u plus s of t of v, which is st of u plus st of v. To show this is preserved scalar multiplication. That's also pretty straightforward. We can first pull because c is a constant. Should be a constant. That's just a regular c. So we can pull it outside of the t. Again, because t is a linear transformation, and then because s is a linear transformation, we can pull it outside of the s. So this is c times st of u. Okay, so st is a linear transformation. Okay, and so, all right. Now the other part is, well, why do these matrices work? Well, and we're going to see very quickly. Of course they do. St of v is St of v, but T of v can be written as At times v. Okay, where At is the standard matrix of T, and then this is now going to be a vector. We're applying S to it, so this is going to be As of At of v, and then by the associativity property of matrices, this is As At v. Okay. All right. So this there's only one standard matrix that will work for each linear transformation. I should have said that the standard matrix is unique. How it's defined. So this has to be equal to AST. To give a specific example of this, let's say if we defined, just to show you how this works, if, let's say, T of xy was defined to be minus y, x plus y, and S of xy was equal to 2x plus y, x. Let's compute the composition two different ways. If we compute it directly, T of xy, what would that be? So this will be S of txy, which is minus y, x plus y. Okay, and then this, now what does S does? S takes whatever it's given and it multiplies the x coordinate by 2 and adds it to the y coordinate. But the x coordinate, or the first coordinate, is actually y, and the second coordinate is x plus y. So this is going to be 2 times minus y plus the second coordinate, which is x plus y. Okay, and that's the first coordinate. And then the second coordinate is just going to be the first coordinate you're given, which is minus y. And if you do a little simplification, this is minus 2y plus y, that's minus y and then x. So this will be x minus y minus y. Okay. All right. And so this is, I think you can see that this can be written as 1, negative 1, 0, negative 1, xy. Or you can just find the standard matrix by plugging in, E1 and E2, and you'll get this matrix. And let's just see what we can see from here, that MT is going to be 0, minus 1, 1, 1. And here MS is going to be 2, 1, 1, 0. Okay, do this. And then if we multiply these two together, and I guess we should call this, we should call this A to be consistent. So, but if we multiply the AS AT, this is going to be 2, 1, 1, 0 times 0, negative 1, 1, 1. And if you multiply this together, you get 0 plus 1 is 1, negative 2 plus 1 is negative 1, 0 plus 0 is 0, and negative 1 plus 0 is negative 1. And that's exactly what you get over here. So this is AST. Okay. So this is the composition of matrices corresponds to the matrix multiplication of the standard matrices. Or I should say, composition of the linear transformations. Is that what I said? Hopefully that's what I said. Okay, we're going to close this lecture with something neat. Hopefully you think it's kind of neat. Another application to trigonometry. So probably the most unpleasant part of trigonometry was memorizing all those formulas, and probably the most unpleasant formula to memorize was the one for the sum or difference of two angles. That is the sine of the sum of two angles and the cosine of the sum of two angles. Okay, and unless you use it a lot, whether if you're an engineer or a teacher, you're not going to really memorize that. And to be honest, I don't really have it memorized completely off the top of my head right now because I haven't been teaching trigonometry for a while. But what I want to show is that linear algebra gives us a way to kind of derive these formulas. And we're just using the fact that with rotation. So if we take let's say we have two rotations, r theta 1 and r theta 2. Okay, and I think we do if we rotate something through theta 2 degrees and then rotate it through theta 1 degrees, that's the same thing as rotating it through theta 1 plus theta 2 degrees, right? Okay, if we have if we rotate it through 40 degrees and then rotate it through 30 degrees, that's the same thing as rotating it through 70 degrees. All right, so we know this is true. So then this should tell us that the matrix for r theta 1 times the matrix for r theta 2 is going to be the matrix for r theta 1 plus theta 2. Okay, and so we know that this is going to be cosine theta 1, sine theta 1, minus sine theta 1, cosine theta 1. And then we multiply this by cosine theta 2, sine theta 2, minus sine theta 2, cosine theta 2. Okay, so those are these two matrices. And then the matrix representation for r theta 1 plus theta 2 will be cosine of theta 1 plus theta 2, sine theta 1 plus theta 2, minus sine theta 1 plus theta 2, and cosine theta 1 plus theta 2. Okay, and now we just multiply this. And if we take the 1, 1 entry here, first row, first column here, and the first row, first column here, what we get is cosine theta 1 times cosine theta 2 plus negative sine theta 1 sine theta 2 is equal to cosine of theta 1 plus theta 2. Where have we seen that before, right? All right, and of course this is plus negative, so this is the same thing as saying this is minus times the, so cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2 is the cosine of theta 1 plus theta 2. And then if we go and take the first row, second column, we get sine theta 1, cosine theta 2, plus cosine theta 1, sine theta 2, and that's going to be the sine of theta 1 plus theta 2. Okay. All right, so these are those dreaded trig formulas that we had trouble memorizing, right? But now we've essentially derived this from linear algebra, okay, and a little basic trigonometry that we used before when we were drawing those circles, okay. And these are nice because now if you let theta 1 equal theta 2, you get some double angle formulas and stuff like that. So a lot of formulas just flow from these. So by the way, this one on the information on this sheet, this won't be on any of our tests, okay? But I just wanted to show you a neat little application. All right, thank you, and we'll see you next time.